Have you ever stopped to wonder what's really going on when you bake a cake? Or why that shiny new nail you left outside is suddenly all rusty? Well, believe it or not, the answer is the same for both. It's all about chemical reactions, and that's what we're diving into today. Okay, here's our game plan. We're going to start with the basics, what a reaction even is and how you can spot one. Then, we'll get into the four main patterns they follow. After that, we'll talk about the energy that fuels them, and finally, we'll look at how to speed things up. Let's get into it. It's a great question, right? They seem like they're from completely different worlds. But really, both a cake and a rusty nail are just perfect examples of chemistry in action. You start with one set of things, and through some invisible magic, they transform into something totally new. All right, so what's actually happening when that change is so dramatic? Let's peel back the curtain and get right to the heart of what a chemical reaction really is. At its core, it's all about transformation. It's a process where the original things, we call them reactants, break apart their old bonds and then completely rearrange themselves to form brand new substances, which we call the products. So, how do you know if a reaction is really happening right in front of you? Well, what's super interesting is that you don't have to guess. Chemistry gives us these really obvious, visible clues or indications that scream, hey, a reaction is happening here. Okay, first clue. A totally unexpected change in color. A great example is when you heat up red mercury oxide. It doesn't just glow red hot, no, it completely transforms into this silvery liquid, that's mercury, and releases oxygen gas in the process. Another dead giveaway is seeing a gas appear out of nowhere. I mean, if you drop a piece of zinc into some acid, you'll immediately see all these bubbles fizzing up. Now, that's not boiling. That's brand new hydrogen gas being born right before your very eyes. Sometimes you can literally feel a reaction happening. Some reactions give off a ton of heat, making whatever container they're in feel really warm. But others do the opposite. They actually suck in heat from their surroundings, making things feel icy cold. And finally, maybe the most dramatic clue is when a solid just appears out of thin air. It's wild. You can mix two perfectly clear liquids like silver nitrate and hydrochloric acid, and boom, a new solid called a precipitate instantly forms and makes the whole thing cloudy. Okay, so we know the signs to look for, but what's actually going on underneath it all? Well, it turns out that most reactions follow one of just four basic patterns. Let's dig into the first two: combination and decomposition. The easiest way to get these first two is to think of it all like a big dance. Just imagine all the elements and compounds are dancers out there on a chemical dance floor. And this slide just lays it out perfectly. On the left, you've got a combination reaction. That's where two individual dancers, A and B, find each other and form a new couple, AB. And then on the right, you see the exact opposite, decomposition. That's when one couple, AB, decides to break up and go back to being individuals, A and B. And here are some real-life examples. If you heat up some iron and sulfur, they combine to make one single new thing, iron sulfide. But if you heat up copper carbonate, it does the reverse. It decomposes, breaking down into two simpler things, copper oxide and carbon dioxide. All right, let's keep our dance metaphor going. What happens when the dancers on the floor start swapping partners? Well, that brings us to our next two major types of reactions, displacement and double displacement. So in a single displacement, you've got a lone dancer, A, who sees a couple, B, C, and just cuts right in, stealing C and leaving B all alone. But in double displacement, oh, that's a full-on partner swap. Two couples, AB and CD, just switch partners and waltz off as two brand new couples. But wait, who gets to cut in? It's not just random chaos. It's all decided by this chemical pecking order called the activity series. You can think of it like a popularity contest. Any element higher up on this list is more reactive and has the power to kick any element below it out of a compound. So we've got the dance moves down pat. But what about the music? The thing that powers the whole dance? Well, that's energy. And every single chemical reaction involves some kind of change in energy, which we usually notice as heat. Reactions basically fall into two camps when it comes to energy. You have exothermic reactions, which are the givers. They release heat out into the world. We show that with a plus sign. Then you have endothermic reactions. They're the takers. They have to absorb heat to even happen, which we show with a minus sign. And you can totally feel this for yourself. Adding something called quicklime to water is super exothermic. It gets really hot fast. But then on the flip side, Some reactions, like trying to get nitrogen and oxygen from the air to combine, are so endothermic they need a massive jolt of energy, like a lightning strike, just to get them to go. Okay, last big piece of the puzzle. What if we want a reaction to go faster, or maybe even slower? Let's talk about how you can control the speed of these transformations by bringing in a kind of chemical coach. And that coach is called a catalyst. Think of it like a chemical matchmaker. It's a substance that helps the reactants get together and change into products way more easily and quickly. But, and this is the cool part, it doesn't actually get used up in the reaction. It's still there at the end, totally unchanged. A classic example of this is with hydrogen peroxide. If you leave it alone, it breaks down super slowly, but you add just a tiny pinch of manganese dioxide, that's the catalyst, and whoosh, it fizzes away like crazy. Catalysts are absolutely vital everywhere, from the catalytic converter in your car to the enzymes in your body that are basically making life happen right now. So, what's the big takeaway here? It's that all of these incredible changes we see all around us, they're not random magic. They're a dance. A predictable, really fascinating dance that's governed by just a few key patterns of coming together, swapping partners, and breaking apart. All of it powered by the flow of energy. Seriously, think about it. Whether it's the sizzle of food in a pan, the slow rusting of a bike, or the silent work happening inside a battery, these patterns are everywhere, all the time. So now that you know the rules of the dance, which reaction will you be the first to spot?